So continuing in the spirit of overview that John has given us, I'd like to talk about a kind of an intersection between information theory, inference, and evolution, trying to sort of signpost some aspects of this intersection, both obvious touchstones for us all to connect on. So a few maybe non-obvious things, where a big part of this, I think, is seeking common language about the pieces that are really bridging all three of these, so that we basically have, in our discussions, a real strong vocabulary to share. I personally feel that statistical inference provides a nice kind of bridge between information theory and evolution on the one hand, basically because you can make those connections very explicit on both sides to statistical inference. And I'll try to organize around a few themes that are very central to the whole workshop, namely this question of entropic limits, both on information rate and total information bound, then classifying distinct types of what you might call information machines or information dynamics that appear to be useful for describing both inference and evolutionary processes, and also try to give a bit of an example of how one might start to study some of these potentially novel dynamics using sort of mainstream simulations, sort of large field of evolutionary game theory problems provides kind of a playground for starting to study these dynamics. So, just starting from this equivalence that John mentioned between Bayes' law and discrete replicator equation, let's just define that we have some population of elements G with initial population values P, and that undergo some series of replication rounds with replication factors that I'll just call F, like F1, F2, et cetera, for different members of the population, such that at some time Tn, the population value for the ith element G sub I would be our initial population times a product of these replication factors.
So all meant to be F1s?
So these are, sorry, F1 should be Fi, sorry, Fi of T1, T2, Tn. Sorry. So then let's also just say that these F are drawn from some probability distribution, and we seek some kind of law of large numbers convergent average for this process. So we do the obvious, turning the product into a sum via taking the log. And then we have a law of large numbers estimator with a guaranteed law of large numbers convergence to the expectation value of the overall process that we're sampling with explicit probabilistic bounds that we can write down. So obvious application here is Bayes' law, in which the actual sampling process is some observable. I'm going to write it as if it's one-dimensional trivial case, but obviously normally this would be some kind of high-dimensional observable. And we are drawing samples of it from some source distribution, and we're defining our replication factors now as likelihoods. In other words, the elements of our population are now models, and so each individual model I, which I'm here indicating psi I, has some likelihood model for the likelihood of the observable given that specific model. So these become our replication factors. So when we take this product that I was talking about in the numerator and summation over all possible models in the denominator, then that's basically Bayes' law. And the only point that I want to make is that this product, the sufficient statistic for this whole process then is simply this estimator that I just defined as basically being the sample mean on this, in this case we call it log likelihood. So I'm going to refer to this as basically an empirical log likelihood, and we can simply set a 0 point for this using the marginal distribution for our observable, and then I'm going to refer to this as an empirical information, basically prediction power for some specified model relative to the 0 point defined by the marginal. Okay? And some of the motivation for choosing that as a 0 point will emerge when you compare it with mutual information. So just to take a big step back into the standard information theory metric, mutual information, let's talk in the same terms that John was using about there being some true but unknown distribution omega, and there's some big set of possible omegas. Let's say we're now looking at a specific inference problem, in other words, some specific omega star drawn from this big distribution of omega, and we draw some actual observations from it. And I'll refer to this as a training versus test sample of observations, basically to learn, well, how much can we learn from our training about basically predicting this observable, and we could actually test how well our model performs, for example, on a test set of observations. So here's a really trivial kind of question. If we try to use the equation for mutual information on this specific sample of data, as I just described, drawn from a specific omega star, what are we going to get? Well, it's going to be 0, because sort of by definition, these observables being drawn from a source distribution determined by omega, so the mutual information conditioned on omega, they're basically conditionally independent given omega. So one way of just emphasizing that mutual information really acquires meaning only in the big picture, where you could sort of think of it like, we're summing over all possible universes omega. We're not talking about one specific omega. It's very important to bear that in mind when we talk about mutual information. Whereas when we're talking about one specific inference problem, omega star, it's like, this specific universe, we could call this sort of a little picture. And an obvious question is, can we get an estimator of the big picture mutual information from one little picture data set? So if you just take this empirical information estimator that I just defined, and you ask what is its expectation value basically over the big picture of all possible omega, you do the usual separation entropy term and paired relative entropy term, a little bit of algebra. Basically what we get is the mutual information for our training data versus our observable minus a relative entropy term. If we consider basically as our model converges to the best possible model, this relative entropy term is going to vanish. And so basically the expectation value for the empirical information basically just is the mutual information. And that makes sense because Basically, that's the limit, the best possible prediction you can do, right? So one way of thinking about this idea of the sampling, go ahead.
Just on this topic, just as an aside, about a year and a half, 2 years ago, there's actually a special issue of the journal Entropy that was all about estimating information theoretic quantities like mutual information from a limited number of IID samples of the underlying distribution. And there's actually a fairly long literature. People these days are looking at things like Dirichlet processes and broken stick processes, things like that. A bunch of other stuff. One has to worry about the biases that are introduced in higher literature.
Sure, for the empirical estimators in effect.
Well, empirical is actually never used. People use it for statistics reasons.
In other words, that you always assume a model underlying.
Well, you can do it different ways. There's Bayesian approaches in which there's Bayesian priorable probability distributions. So you use Dirichlet processes come from. But there's also where people try to correct to make it be as low, to basically take care of bias plus variance issues. So they introduce these correction terms. It goes back to some work by Grasberger.
But just so I understand, the approach is that you have some family of distributions as your underlying model for the data?
The Bayesian approach, yes.
Mm-hmm.
The non-Bayesian approach, it depends on which non-Bayesian approach you look at.
Yeah, I mean, I think it's interesting to at least as a point of reference, look at a model-free estimator. Okay, so the only point here being that you can think of this empirical information definition, totally sampling-based estimator, as being like a sampleable form of mutual information in the sense that we can take one specific inference problem, actually get an estimator from that, but if we looked at how that estimator on multiple problems, the average of that estimator would converge to the mutual information. So obvious second version of this, I think Mark pointed this out some years back, that there's this sort of analogy between Bayes' law and the discrete replicator equation. So now we're basically replacing our likelihood of the observation by basically a replication number, which I guess you would call fitness, and the extension to multiple observations in Bayes' law would now be multiple generations. And again, the empirical metrics that I defined are the sufficient statistic for that sampling process. So we can kind of formulate what you might think of as an operational definition of a machine cycle, where basically the machine consists of a population whose weights represent the actual computation of an empirical information metric. In other words, the machine is calculating the empirical information metric. That these empirical information metrics are the sufficient statistic for the evolution of that system, and that this is an iterative cycle. You could sort of think of this as being operational in the sense that there's an actual sampling process that's making the measurement, and that what we're calling information, this gradient, is what's driving the evolution of the system. Okay, so one really simple level of that is at the strictly local gradient level, where we basically have just these two ingredients in our machine cycle of sort of placing your bets of what's going to replicate best, predictions for the future, and then actually drawing a test sample. The whole point of calling this empirical is that you get what you pay for. In other words, if you don't sample, you don't gain any information about the things that you don't sample. So it's really limited by just strictly local gradient that's actually sampled, which very obviously, typically we would assume does not include the genotype with maximum fitness. So you could sort of think of this level of an information evolving machine as sort of having a tunneling problem. That is to say, if the path to G star basically passes through a whole long distance of low fitness states, then the rate of transition to G star, you could think of this as being sort of exponentially slow. So I think I'll talk about a few limits on this. First, in terms of just the rate, just to point out that in fields like computer science, there's a pretty broad usage of a model selection approach in which effectively we're searching for a maximum of some metric, basically like empirical information. A maximum likelihood is basically equivalent to that. So, as I emphasized before, the law of large numbers is what's sort of holding all this together. In other words, if the sampling-based estimator actually deviates from the expectation value across the whole set of the distribution, beyond sort of some well-defined small deviation, then our whole foundation for picking models based upon this sample value being high breaks down. And then that's exactly what happens, of course, when you do model selection. You're actually selecting for maximum deviation, right? Because we're searching, in effect, some very large space. I don't want to dwell on this too much, but basically the kinds of corrections like Akaike information criterion or Bayesian information criterion, they don't really eliminate that problem. They just cordon off certain pieces of it. If you go and use those metrics, you still find overfitting. So one kind of simple way of stating this is that when we go back to this expectation value expression and now focus on the relative entropy piece of this, basically we have a pretty clear statement that we maximize our prediction power when the model that we're using actually converges to what you might call the posterior likelihood. In other words, the likelihoods mixed with simply the Bayesian posterior. So you can think of this, an attempt to go below the entropy of that mixture will, on average, always degrade prediction power. Okay, so in the interest of time, I'm not really going to dwell on the nice aspects of this posterior likelihood, but simply fast forward to a second of these sort of entropic limits. Again, in the Bayesian case, we can't assume that we actually have the correct model omega star in the set of models that we're actually searching. So we have this sort of Bayesian relativism that all you can really calculate are odds ratios. And Bayes' law really doesn't have an answer for telling you whether your current best model is good enough or really horribly far from good enough. And the basic thing that solves this problem is when we basically ask, what is the bound on maximum prediction power possible for this observable? And this is sort of the case where this question of being able to have an empirical estimator of the entropy of the observable basically allows you to define what you might call potential information. In other words, that sort of the latent prediction power remaining in the observations not yet captured by the best model that you have. And again, there's a kind of law of large numbers convergence for this with bounds that you can compute. Interest of time, I won't dwell on this. But basically, you can think of this as being sort of analogous to potential energy in the sense that for a given target observable, the sum of the empirical information and the potential information is a constant. That is to say, when you start out that is all potential information, and as you model it better and better, you're converting potential information to empirical information, but you can never exceed that total information bound. Okay. So one sort of example of this in the real world is if you have, high-dimensional vector-like protein sequences, for example, and you now use words drawn out of that as an observable that you now measure an empirical entropy estimator on. Basically, you find that short words outperform long words, basically because they're much less sensitive to the effect of insertions and deletions. And when this process will identify words with high potential information driven by unusually low empirical entropy, and then you apply a mutation model to this to basically convert that potential information to empirical information. That is just with substitution of words exactly what the BLAST sequence homology search algorithm is doing. So the idea is useful. So this gives us kind of a second level of machine where now we're explicitly estimating potential information and seeking basically to incorporate it into our model in a fairly direct way. And even at the level of just using the empirical density with extrapolation and interpolation as our model, you can see that in effect this opens the potential to tunnel rapidly to the true distribution omega star, basically through this direct detection and modeling of the potential information. Okay, a third metric that I want to introduce is the idea of disinformation as the reduction in some target information involving machines' prediction power, basically just by sending it a signal. So you could break that down to the initial signal that's sent, and let's just call that the deception signal. And then there is a sampling process where we're actually going to measure the disinformation. And you could think of that as basically the exploit sample. Okay? So we're basically measuring the reduction in prediction power on that specific exploit sample. So a simple example of this would be kind of a bulk mail investment con where the target IEM is an individual investor trying to predict whether some particular investment will win, like stock market will go up next week. And an initial deception signal would be basically, take 10,000 people, send half of them prediction it's going to go up, half of them that it's going to go down, and then week by week, reduce the number of people you send predictions to based upon the ones where the predictions turned out right. And the exploit sample would be, after 5 weeks of that, send them a request for money for your next prediction, with them now having basically a disinformation metric just being the money that you receive, since the actual predictions have no predictive value. And that's a sort of classic example of problems of model selection. Obviously, there's lots and lots of examples in biology of this sort of disinformation attack. I won't dwell on that in the interest of time. But basically, just to emphasize that when you have interaction between one machine versus another machine, you have a new kind of dynamic, basically where there's an interesting kind of pairing of selection pressure here that tends to induce multiple rounds of arms race. Okay? Basically, if the target of the disinformation attack is some feature of high fitness value to the target machine, there's going to be both strong negative selection for retaining that original function, plus positive selection for escaping the very specific disinformation attack that's now being applied as a new pressure. Whereas for the attacker, there's now going to be positive selection for beating the latest escape and being able to regain some kind of disinformation attack value. So I would argue that this kind of dynamic, where both of your players are themselves information evolving machines, and now they can have this kind of disinformation dynamic between them, introduces some interesting changes in what the whole system can do that you might call a multi-scale information evolving machine. In other words, where the individual population elements are themselves information evolving machines. So you could consider the whole system would be like, you know, an ecosystem, and the individual information evolving machines are then individual species. So this basically, you could think of it as being an interesting tunneling mechanism. So just in ending, I'll maybe briefly show you an example of trying to start to investigate whether this kind of idea of introducing information players into an evolutionary game theory problem produces any kind of interesting dynamics. And the basic idea here is that we just define a new kind of player that is itself basically a little inference machine, right? So it is itself an information evolving machine that's trying to estimate basically the strategy vector for its opponent. And we tried to look at this in a really standard kind of evolutionary game theory context, you know, standard game, prisoner's dilemma, defect versus cooperate as the only choices. And the reason that this seemed interesting is that within the evolutionary game theory literature, especially recently, there have been quite a number of assertions that sort of pure first-order Markov strategies are kind of, you know, the be-all and end-all. For example, the claim that a zero-determinant first-order Markov strategy would be universally robust. In other words, no invader of any kind could achieve better than neutral fixation probability. Sort of, you know, if you take these first-order Markov, you know, they're not information evolving machines. They don't have any internal states, so they don't meet the definition. It's a question, you know, could information have any value in this kind of classic evolutionary game theory sort of simulation? So, you know, two kinds of very basic things that having an inference player open up. Number one, the possibility of self-recognition, so that you basically play different with yourself than with opposing types. And second, that you can choose a different strategy depending upon what fraction of the population, the total population, your type makes up. And that turns out to be a pretty significant effect. So here, population fraction on the x-axis and relative fitness difference versus a so-called robust zero-determinant player on the y-axis, where positive basically means the information player is gaining a fitness advantage. Really interesting pattern that you see repeated over and over again is basically at low population fractions for the information player, its optimal strategy is to cooperate, basically to induce cooperation from the resident population. Whereas basically once it gets into the majority, there's a clear switch to basically defecting against the opponent to achieve a maximal resident advantage, which I won't go into any details about, but you can read more about this on arXiv. So I won't really dwell on the details of how it does this, apart to say that, you know, these basic ideas of self-recognition and population sensitivity are basically core to this. And to make a long story short, that the information player versus you know, sort of the usual suspects in this case in prisoner's dilemma, it achieves much better than neutral fixation probabilities, essentially near maximal compared with the best of what other player types can achieve. Whereas by contrast, these Markov first-order strategies, the kind of best in the field, basically have never been observed to be able to invade an information player population, basically because the information player is able to achieve a fundamentally different level of resident advantage, which really requires this information player property. So I'll just end by saying that I take from this experience that introducing the idea of an information evolving machine versus information evolving machine dynamic into evolutionary game theory studies seems to reveal some dynamics that people within evolutionary game theory weren't really prioritizing. And in particular, I'm extremely interested in disinformation as a dynamic that I feel is extremely interesting as a subject for evolutionary game theory studies. But my sense, just in closing, in talking with people in evolutionary game theory, is that initially that's not where their heads are at. So to a first order of approximation, if people are interested in this, there's sort of not yet a community. We have to form a community if we want to move an idea like that forward. So I'll just end there and take any questions. Just emphasize that the information player work has been done with Mark Harper, Daschle Fryer, and myself, with funding from the Department of Energy. And if people are interested in the details, I'll post some links up on the NIMBioS blog.